We're really excited to be welcoming to the stage Technical Product Marketing Manager at NVIDIA to talk about speech AI demystified. Please help me welcome Sirisha Rella to the stage.
Hi, everyone.
Hi, Sirisha. Well, great to have you with us today and looking forward to the talk. The stage is yours.
Thank you. Thanks for such a warm introduction. Hi, everyone. We have only a couple of minutes left, so I'll directly jump to our topic, speech AI. So let me share my screen and we can get started. Yeah. So as you all know, voice is the common interface that we use to communicate, and that's the reason every day hundreds of billion minutes of speech is generated. And speech AI can help digitize these conversations. Let it be you talking to a digital human in metaverse world, or talking to a real human in call centers, or even talking to your colleagues in online meetings. So when I say speech AI, it basically includes two technologies, automatic speech recognition and text-to-speech. So the interesting fact here is these are not new technologies and existed from last 50 years. So let's take a look at how it all started and where we are today and how the future is going to look like. So coming to evolution of automatic speech recognition, the first system was introduced in 1952 by Bell Labs, which is called Audra system. And this system has the capability to transcribe only digits, which means the vocabulary size is only 10. So what that means is that vocabulary size is basically the number of words that a system can understand. And the next on the timeline is IBM Shoebox, where this system has the capability to transcribe words. However, it does it in isolated fashion, which is very unnatural because as humans, we don't pause after each word in general conversations. And in 1976, Carnegie Mellon University introduced Heartbeat, a system that is capable to handle continuous speech. And the vocabulary size increased to 1,000 words. However, in our dictionaries, we have hundreds of thousands of words. And comparatively, this is still a small vocabulary system. And in 2000, statistical algorithms came into existence, and this has a capability to handle tens of thousands of words. However, the problem with statistical algorithms is that, firstly, accuracy has reached to a stable stage. Even if companies wants to further enhance their accuracy, they weren't able to do it. And secondly, the statistical algorithms pipeline is complex. And one of the reasons is because force alignment data. So in layman terms, force alignment data is given a text transcript of an audio segment, you need to determine in what particular time a word is occurring in that audio segment. So you need to have that tight force alignment data to develop these statistical algorithm pipelines. And in 2014, deep learning came into play, addressing some of these challenges, and it revolutionized the way ASR is done. Firstly, the quality is enough that companies were able to deploy deep learning ASR in production. However, there are a couple of areas deep learning ASR developers are trying to enhance the pipelines for. So firstly, industry-specific jargon. Let's imagine an ASR deployed in a healthcare industry. The pipeline needs to be able to transcribe sentences like maybe chest x-ray says that left retrocardiac opacity, and this may be due to athletics, aspiration, or early pneumonia. Understand there are so many healthcare related jargon here, and so depending on whichever industry it is, let it be healthcare, telecommunication, or finance, the ASR need to transcribe them accurately. And coming to multilingual dialects and accents, if companies want to play big and want to expand their solutions globally, these pipelines need to understand multiple languages, dialects, and accents. And then coming to noisy environments. So in today's world, most of the people that are interacting with these applications have noisy environments. For example, just imagine a person who is calling to a call center. I don't think he's going to be in a quiet place as if he's looking for a place to meditate. And how many of you have background noisy environments while you are talking in online meetings sitting at your home? So these pipelines, ASR pipelines needs to be noise robust. And coming to contextualizing words, so there are homophones, right? So homophones are basically the words which sound same, but their meaning is different. For example, peak of the mountain versus let's speak at something. So the peak in both of these sentences sounds same. However, the context is completely different. I mean, the meaning is completely different. So the ASR pipelines need to transcribe these words accurately depending on the context. So moving on to evolution of text to speech, it has a similar story as ASR and it existed from last several years. So the way TTS is measured is based on how human-like the generated synthetic voice is. I'm going to play the first text-to-speech system and then deep learning-based text-to-speech, and you can see it by yourself on how deep learning-based text-to-speech sounds more lifelike. So it's basically saying, I know it's difficult to understand, but then it's basically saying she saw me. And then this is deep learning based text to speech.
You will be receiving a text message on your phone confirming the details of your order.
Yeah. So if you can observe the deep learning based voice, it has that human aspect to it, right? It has the pitch, speed, and intonation, when to raise the pitch and when not to. So and also coming to deep learning, TTS developers are also working on and improving a couple of areas such as real time and human like voices and controllability. So coming to real-time and human-like voices, so basically the TTS pipeline has key deep learning models in addition to non-deep learning components. And to generate a human-like voice, all these need to work together in real time in under very few milliseconds, because you can't ask a question to an application and then wait for several seconds to hear a response. And coming to controllability, of course, the pipeline should be flexible enough to control the paralinguistic elements, which are again pitch, duration, and the intonation, so that we can make it more expressive depending on our use case. So what really fascinating to me is that some of the companies already made a significant stride in deploying speech AI in production. So I'm going to talk about three such compelling use cases. The first one is T-Mobile. So their use case is expert assist. So they're using ASR to transcribe the conversations between customer and agent and analyze those conversations to provide real-time recommendations to agents. And of course, what they did is they also fine-tuned the models and pipelines on regular cadence to make sure that the pipelines understand their domain and industry-specific jargon, like whenever customers are calling to their call centers. And coming to Tartil AI, they have an application that helps users to recite the Holy Book Quran. And they're using Arabic ASR to identify the errors that users make. So, of course, they did not build the model from the scratch. Instead, they took a highly accurate model and fine-tuned on an Arabic data set to make it work for Arabic. So Data Monsters has a similar story and then focuses on children's reading tutor application. So if you want to learn more about speech AI, we provide starter kits for both speech recognition and text-to-speech. And if you want to receive latest news about NVIDIA speech AI, you can scan the QR code on my screen and then sign up for the newsletters. Yeah, that's all I got. And thank you for having me here.